This is the slow motion video of the clip that you just saw. On the right are graphs of position versus time for both the x and the y positions. We will take a look at what these graphs mean and the energy involved in the motion of the car.
What we have here is a position versus time graph. The blue line is the x position, and the green line is our y position. Basically, we know from derivatives and things that our velocity is the slope of the lines, and we will analyze that later on. So what you see here, between about 5 and 6 seconds, we have a relative minimum for our y position, and that's just basically where the race car hits the bottom of the loop. We have a relative maximum here right around 0.8 seconds, and that's the top of the loop. We go back to the bottom of the loop here again, and this is not the top of the loop because after right around 1.2 seconds-ish, we actually go into projectile motion. So this is more of a parabola. Now we'll analyze the velocities. What we have here is velocity in the y direction is the green line. And as you can see right around here where we reach the bottom of the loop, our velocity in the y is right about 0, and that makes sense because we are at the bottom of the loop and we're about to go back up. Then right around 0.8, we're at the top, and our velocity in the y again is the same because we've hit the top and we have to go back down. Then it's 0 again, right around here. And then at this point we go into projectile motion, and we notice it has a negative slope, which means our acceleration is negative, and that would be due to gravity. Our velocity in the x direction, which is the green line, right around our 0.54 seconds here, has a relative maximum, and that makes sense because that is the bottom of the loop, and that's when it's going to be going the fastest. And we also have the highest v squared term, which means our kinetic energy will be the highest. When we reach the top of the loop, we have a lower kinetic energy because our v squared is low, but it's not 0 because we still have a velocity term in the x direction, even though it's negative. Then we have another relative maximum, but as you can see, the v squared term has decreased significantly, even though it doesn't appear that the velocity have changed all that much in difference. It's still around 0 and it's still around the same point, but our kinetic energy has decreased significantly at this point. Then again, in the projectile motion, we notice that our x velocity is constant, and that would be to be expected if there's no acceleration due to position on the track being affected by the normal force. Alright, and last we have an energy diagram. The total energy, which is the sum of all our initial energies, which is basically just our initial potential energy, has to be constant for the entire system due to the law of conservation of energy. So we have our kinetic energy is this green line, which we saw before, but now it's just multiplied by 1/2 of the mass times v squared, which we saw. And then we have our potential energy, which is just mg times our y value as a function of time, which we also saw a line that looks like this before with our y as a function of time. And we have a new line, which is this blue line, which is the sum of the two. And we notice that it decreases slightly here. I mean, you see this noise, that's just due to the approximation of the derivatives. And then it decreases and plateaus off again here when we had our highest speed, so the work due to air resistance causes a decrease in energy.
Now that we know what a perfect run looks like, let's take a look at the energy involved in both a perfect run and a failed run. We will begin by calculating the starting height required for the car to make it around the loop in ideal conditions.
Here is a diagram of our track. It has height h and radius r. The equation for work is work from point 1 to point 2 equals the integral from 1 to 2 of force times change in radius. Some of the energy that is involved here is gravitational potential energy. The equation for this is potential energy equals mgh, which is mass times the constant g times height. Given these equations for work and force and vertical position, we find that work is equal to the final potential energy minus the initial potential energy. Another type of energy involved in our experiment is kinetic energy. The equation for kinetic energy is kinetic energy equals 1/2 mv squared, which is 1/2 times mass times velocity squared. Given these equations for work and force and velocity and change in radius, we find that work is equal to the final kinetic energy minus the initial kinetic energy.
Now, in order to calculate the velocity needed to make it around the loop-de-loop at point 2, we compare the energies and height at point 1 and at point 2. At point 1, h1 equals h, which is the height above the bottom of the track, and the potential energy 1 is the mass of the car times gravity times h, and the kinetic energy at point 1 is 0 because the car is not moving. At point 2, the height is 2 times the radius of the circle, the potential energy is the mass of the car times gravity times twice the radius of the circle, and the kinetic energy is 1/2 the mass of the car times the velocity squared, and we are looking for that velocity. The equations for circular motion are v squared over r equals a, which in this case equals g. V squared equals gravity times the radius of the circle. The kinetic energy at point 2 equals 1/2 mass of the car times gravity times the radius of the circle. Conservation of energy is energy initial plus energy added minus energy lost equals energy final. The energy initial and energy final can be broken into kinetic and potential energy. E initial is broken into kinetic energy 1 plus potential energy 1, and energy final is broken into kinetic energy 2 and potential energy 2. Energy added is 0, and energy lost is due to the work done by friction. In our case, there is no work done by friction because we are imagining the ideal case, and there is no kinetic energy 1 because the car is not moving. Therefore, it simplifies to potential energy 1 equals kinetic energy 2 plus potential energy 2. And that is mass of the car times gravity times height equals 1/2 times mass times gravity times the radius of the circle plus mass times gravity times 2 times the radius of the circle. The mass is cancelled out, gravity cancels out, and you are left with h equals 1/2 r plus 2r, or 5/2 r equals h.
Based on the equations we had before, we need to release the car from a height of 5/2 times the radius of the loop-de-loop in order for it to make it around without leaving the track. In our case, that's 40.3 centimeters from the base. As you can see, it doesn't work out. The car falls off the track because we had other forces acting on it, like friction and air resistance. So we calculated that in order for the car to actually make it around the track without leaving, it has to go from a height of 55.9 centimeters above the base. Now, if we start the car from anywhere in between the two, it still doesn't quite make it around without leaving the track.